All right, so today we're going to start a discussion of effective actions. There will be two lectures this week on effective actions, and we will get to normalization group. As usual, if there are any questions, please do ask along the way. I don't know whether you... All right, so what did we do in the last couple of lectures, actually the first 2 weeks of this semester? We talked about renormalized perturbation theory, right? So what is the basic idea? The basic idea is you take bare fields. These are the things that put into the Lagrangian, right? Initially, phi naught of A, and write them as some renormalized field up to some wave function renormalization. So there's a wave function renormalization parameter Z for every field. Then you take the bare Lagrangian, which is now a function of bare fields and bare coupling, right? This is a renormalized one, plus the counter terms. Whatever the counter terms are, what is the difference between the two, right? So far, it's completely arbitrary. Now, what we do is then we're gonna we did perturbation theory in this, right? We did Feynman diagrams in this. Now we're gonna do Feynman diagrams in these variables. That's exactly what we're gonna do. And then the counter terms also contribute as like vertices and like propagate. There would be corresponding Feynman diagrams associated with them. We worked out the case of QED, right? Scalar field theory very briefly, and then QED. Now, one of the important things that I want to discuss are the connection between renormalized perturbation theory and symmetries. So for example, even though this is not quite a symmetry, but we talked about word identities. When you have a gauge theory, right? Classically, you have this del mu j mu equals 0. Quantum mechanically, what you would like to do is you would like to promote j mu to an operator, j mu hat. Now, it's not true that del mu j mu hat as an operator is equal to 0. If you put this as an operator inside time order correlators, this becomes 0 up to contact terms. So what is a contact term? Contact term is when, so this O has a bunch of operating positions at various points, and when X is not on top of any of those points, this is 0. But if you put this on top of any of those those points, there will be Dirac delta functions or divergent terms, right? Those are called contact terms for obvious reasons. So an example of this is, for example, like you could pick this operator to be psi bar at x1, x2, and as long as x1 is not on x1 or x2, then this is 0. However, when x1 becomes x becomes x1, there's a Dirac delta function, the coefficient of which is q, charge, right? And then if it becomes x2 is q, but notice that this is the particle and fermion, anti-fermion, so there's a sign difference here on the charge, and then multiply by the 2-point function, the propagator. This is a fully non-perturbative relation, right? So let me actually, before saying a few more words, let me just take a step back and say, repeat what I'm trying to say. So in renormalized perturbation theory, or in general in renormalization, right? What you would like to do, you would like to allow for the bare parameters to be different from the renormalized observable ones, right? However, if there are symmetries, you don't want to introduce too many parameters. If there are symmetries, certain coupling cannot change in particular ways, right? For example, we saw the quantum effect, no matter what they are, they're not going to introduce, they should not introduce any mass for the photon, because that's nonsense, right? That's just, that's gauging, is forbidden by gauge invariance. So gauge invariance is a non-perturbative principle. You want to include that in a smart way when you organize your perturbation theory, right? You don't want to put too many variables. So in the case of QED, this particular word identity resulted in a non-perturbative connection between the vertex correction, right, and the propagators So this is the Ward-Takahashi identity that relates the full non-perturbative vertex to the full non-perturbative propagator for the fermions. And in the Q going to zero limit, this takes this form. And we said that we saw one manifestation of this. We're going to come back to this later. Also, is that it relates the divergences in the vertex to divergences in the fermion self-energy. Now, we only did one loop calculations. Today, we're going to do a very brief, just play around a little bit with two loop calculations to just see structurally how they act. But the BPHZ theorem is this theorem that guarantees that a renormalizable theory, defined as we defined it, right, if you recall, in a renormalizable theory, a finite number of local counter terms can cancel divergences to all order in perturbation. Right? So here, what is the meaning of a local counter term? Well, our counter terms were what? When we did this, these terms were also local. What is that a consequence of? It's a consequence of the fact that the wave function renormalization is just point by point. The renormalized field, in principle, once we get to our renormalization group, we're going to see this. In principle, something that could occur is that renormalized fields could be some average coarse-grained versions of the bare fields, right? That's a possibility. However, in renormalized perturbation theory, and if that were the case, then our counter terms would be non-local because we're subtracting something that is completely local in phi naught, right? From some expression that's local in phi r, right? But the BPHZ theorem says in perturbation theory, renormalized perturbation theory, there will always be local counter terms that can cancel divergences to all orders in perturbation. This is something to put. So we're one manifestation of that we're going to see today. We're going to do some two loop diagrams in lambda phi 4 and observe the local count terms cancel all divergences at two loop. So I'm not going to do all diagrams. It will be a couple of lectures if I did, but we're going to do two sample calculations that have different flavors, right? Certain diagrams we're going to calculate. And this is to be considered as a build-up towards renormalization group flow. So that's we're going to build in the next part of the course. We're going to talk about renormalization group and all the formalism. And this is all a build-up towards that. Now, before getting to renormalization group, we're going to spend this week talking about something that's called the background field methods. And the goal is, this is like a mini version of renormalization. It's not a mini version, it's like a specialized version of renormalization. And then we're gonna go through this before jumping into full normalization group, non-perturbative. All right, so what is the story? It's called background field methods, and the hero of the game here is a functional called effective action, right? And its raison d'etre is the generating functional of the 1-pi diagrams. So we're going to define what the effective action is, and then I'm going to not prove, but argue, at least for the low point functions, that it is the generating functional of 1-pi diagrams. Hopefully you recall what the 1-pi diagrams are. Now, part of this is, I can't stress this enough, I would love to give you an intuitive picture of effective action. So I'll do my best, right? I'll do my best to give you an intuitive way of thinking about effective action, because it's a very, very useful thing. A lot of practical calculations in quantum field theory are done using effective actions. So let's say I can put it this way, that because, let me take a step back and give you a little bit of motivation. If you're doing quantum field theory, say to one loop, right? What would you like to calculate so that you have everything up to one loop? You would like to calculate the partition function at one loop, right? Then varying the partition function with respect to sources will give you, or the log of the partition function with respect to sources will give you the connected diagrams. It's the same amount of information if you have a generating functional for the effective action. So when we're dealing with certain quantum field theories, somebody goes out there and does the calculations of all diagrams, those integrations, all of that, and the net result is going to be effective action of this theory at one loop. They give you a single functional, the same way that if they calculate the free energy, right, they will give you a single functional. And then that single functional encodes all the quantum effects of that one loop. So you don't need to do the calculations again. That's why it's such a practical thing, right? All right, questions so far? So this is what we're going to do today. And then the next lecture, we're going to spend more time on effective action. I'll try to give you a little bit of a picture, hopefully if time allows, as what is how to think about effective action in relation to renormalization. All right, before doing that, of course, part one of what we're doing is lambda phi 4 to loop. So the simplest thing to start with is scalar self-energy at two loop. Right? So the 1-pi diagram for the scalar self-energy was this that we computed. Right? What was this? It was just integral of dd of p 2 pi d 1 over p squared minus m squared. Right? This is what it was. So I'm going to call this k1 of m squared. We computed this, we calculated this. Well, we regulated this in dim-reg and calculated all of that song and dance. Now, the diagram that we're interested in calculating at two loop, there are these two diagrams that appear. There's this diagram, and then there's this diagram. There's also this diagram, right? Oh, sorry. No. What am I saying? This is for the vertex. This is for the vertex. Sorry. No, these are all the diagrams that there are at two loop. Good. All right. So let's start with this guy. So this is what we're gonna do. We're gonna compute these two. Consider this guy. What is it? Well, there is momentum k. This is p, right? So it's an integral over k and p minus I lambda r squared because there are two vertices, right? There is a propagator for p and then two propagators for k, right? Everyone's with me? So now I immediately see the structure. It's convenient because these two integrals are completely independent, right? I can call this k, if I define kn of m squared as this way, right? This would be k1, and this would be k2, proportional to k2. I think I want to put 1 here. Right? So these are tricks that we use. You can just do this integral once and just recycle it, right? So k1, k2. Good? All right. A little comment. In dim-reg, we saw that there is a pole for k1. We calculated that explicitly. The pole was 1 over epsilon. It's a similar thing for k2. The k2 also, if you go through it, the dim-reg will give you a 1 over epsilon pole, and then together you're gonna end up with 1 over epsilon squared. So this is a new form of divergence. It's not a log divergence. If we did momentum cutoff regulator, there's an integral over p squared and then k squared, right? This will give you a lambda squared, and this gives you log lambda. So the structure of this diagram is lambda squared log lambda. Good. More generally, if you take a diagram like this with n of these bubbles on top, what is the structure of this diagram? How does the divergence behave? Lambda to a power of n, because there will be n vertices, right? And then, so this is n loops. Yeah. And then lambda 2 and log lambda squared to the power of n minus 1. That's the structure of it. Because it's only the last one that looks like this. All the intermediate ones look like this. Right? Good. That was with me. Now, consider this diagram, these bubbles on top of it. Just convince yourself this is lambda of n plus 1, log of lambda squared to the power of n. It's for you. Good. All right. So now those are, of course, our standard diagrams. Now you have to have counter terms. What are the counter terms we could have for the self-energy? There is this counter term. What else do you have? You also have this counter term. These are the two counter terms you have. Okay, so let's calculate this counter term. What is it? Minus I lambda over 2, because there's one vertex. Integral of p, there's a p running in the loop, right? And then I over p squared, there are two of these propagators here and here, right? And then the counter term, this cross, right? That is I p squared del z minus del m. Good. Now add and subtract mr squared del z here, so that p squared minus mr squared del z will kill one of these powers. The coefficient of this will be k1 now. And now that mr squared del z next to this del m will give you a k2. Right? Okay. Very good. Now what are we going to do? We're going to plug in the tree level, the one loop values of del z and del m here to compute this R. Good. So what were the one loop values? Del z was 0, if you recall, and del m was 1. So that means that this diagram becomes minus I del r over 2 del m1 of k2 mr squared. Good. Now let's add these two diagrams. The diagram we had was minus I lambda r squared k1 k2, right? So that's minus I lambda r squared k1 k2. Oh, here is it's important. I'm also putting in the symmetry factors of the diagrams, right? So the symmetry factor of this diagram is 2. The symmetry factor of this diagram is 4, right? They should cancel. Good. But notice what happens. You find this relation. This relation is already what we found for delta M1. So the renormalization of delta M1, so what did we do? At one loop, we had these diagrams. This is a structure that we see over and over again. So we had these two diagrams. This gave us delta z 0 and delta m. I put 1 because that's at one loop, right? It becomes minus a half lambda r k1 of mr squared, right? Then what we have next was we had this. Oops. We considered these two diagrams and saw that because of once you plug in these two relations, they add up to 0. Good. If you think about it, at some level, relations of this type should appear all over the place. Why? Because we said a finite number of counterterms will capture all divergences to arbitrary order, arbitrary loop order. Now, I'm lying a little bit because here delta m had lambda r. Well, okay, no, let me not explain all. The next example will be evident. Good. Questions here? Let's calculate the other diagram. So here's the other diagram. It's a little bit more involved. And you get a flavor of this one. It was so easy that I didn't need to do any calculations. So here's Q, P, K, and then this is Q minus P minus K, right? There's like minus I over lambda R squared, 1 over 6. Do you see that the symmetry factor of this is 1 over 6? You can work that out. There is the propagator for this guy. There's the propagator for this guy. And then the C is the propagator for the middle guy. Good. So first, what we're going to do is the following. We have two integrals now, right? K and P. Let's first focus on the integral over P, right? So we're going to treat this as we're going to try to do the integral over P. The P dependent terms are A and C. What was our first thing we would do? We would just use Feynman parameters, right? So these two guys, we write them as 1 over AC. You introduce a d of x, you split the two guys together, and then you define this new variable, right? As we did last time, so that you could just the standard Feynman parameters. The result becomes the following. It becomes then you could do the integral over P, which once you shift the momenta, and it becomes this, an integral over K. This is 1 over B, right? That's the part that we haven't done. Integral over X of 0 to 1 of K2 of C of X, KQ. Remember that all the structures that we had at the end of the day look like right? And this integral is closely related to my K, right? That's why I could recycle all of these up to some volume factors of, the volume of a SD minus 1. So once the dust settles, this is the structure you find. Now this K2, you just go through the standard expansion near 4 minus epsilon, and this is the expression that you obtain. Well, sorry, it's not quite. You do the integral, and then you get these gamma functions, right? You do the integral in dim-reg. The integral is doable exactly as K2, right? There's a gamma functions, and this is what it becomes, right? Notice that now the epsilon terms are whatever they are, right? This has dynamical content to it. This is the K-dependent part. So now we still haven't done the K integral. We have to put 1 over B next to 1 over C of X to the power of epsilon over 2. This is the integrand for the second integral. Right? Are you guys following me? Now, what we do is, of course, the set of tricks we have are fixed. We do Feynman parameters for 1 over A to the power of B, A to the power of M, B to the power of N. And this is the form of it. This is the form of it. Now, can you tell why I wrote it this way? The reason is this. I have 1 over B times 1 over something to the power of epsilon over 2. If I write it this way, I could treat this as an analytically continue this for arbitrary M and N positive. And that's what we're going to do. We're going to do Feynman tricks for 1 over A, 1 over B times 1 over something to the power of epsilon over 2. Right? This is going to be the answer. And there's often, as always, there's a shifted momentum, right? This is going to be, so this is the structure of it. It's going to be an integral over x. This came out of, there are a bunch of gamma functions. Integral over x came out of the first Feynman parameters. Integral over w came out of the second Feynman parameters, right? And then there are all sorts of powers, but what is down here is mr squared minus w of n, w x minus 1, this factor to the power of 1 minus epsilon squared. Okay, so let's push through. What you do is you define this guy R of X and W, right? What is this? What is exactly this? So what W and X, W is like X, right? Some parameters that we're integrating over from 0 to 1, and so is X. So this is just a coefficient, right? This is mr squared minus q squared f of x omega. Do you remember this structure we had before? Well, we had before, right? We had this delta. What was delta? Delta was m squared minus q squared, this thing, or times 2 or something, right? So what has happened is that this guy, f of x and w, has replaced it. Of course, it's going to be some function of x and w because these are what we're integrating over, and this is just an overall constant, right? So there's really nothing brand new to it. It's just algebra, right? Then what you do is you organize your integral this way, right? An integral over x and w. You don't need to do them. R to the power of 1 minus epsilon. This is the part that we're going to keep track of things. It's singular as epsilon equals 0 because of this guy, right? And then it's divergent as w goes to 0. We extract the pole. This is what it's going to look like. 1 over epsilon squared, as I promised. Okay? Good. So now, this was what we saw that. So very good. Okay, good. Everyone's with me now? Yeah.
The part like right before this was the C also like a new delta. Did you use it that way?
Yes, exactly. I treated that like a delta. It's just
it also has a similar form, just with Q minus K instead.
Exactly. It's mr squared. Well, exactly. This is it. Yeah. There are no new tricks. It's just a repetition of the same trick. And algebra. All right, good. Now, what did we, so now what, we saw that the divergence of these two guys canceled, right? Now, what cancels the divergence of this? How could we cancel the divergence of this? The divergence of this is order lambda squared, right? And it's 1 over epsilon squared. What actually cancels that is, remember when we were doing this calculation? When I wrote this as delta 1 and m1, it was because it was 2 loop, right? And of course, because it's 1 loop, it has a lambda r squared. More generally, what you could say is the following. You could say that this guy, delta z of lambda of r, right, and delta m lambda of r are functions that you expand in lambda r. To the first order, these are the results, but there will be a second order term. The second order term is precisely what will cancel this side. Right? All right. So how do they cancel it? This is a calculation for you guys to do. It's not hard. You just have to do a little bit of algebra. The part that's hard is all I did was just about self-energy. Now, if you want the vertex at 2 loop, you have a gazillion diagrams. You have a lot of diagrams, right? So what are the diagrams that contribute to the vertex at 2 loop? There is, for example, this diagram. Then there is, wait a second, what am I drawing over there? No, this is good. Well, there's this diagram, trivially. There's that. Wait, that doesn't, that's wrong. This has pi 6. This is wrong. This is wrong. There are these kind of diagrams. It's clear why that was wrong because it has pi 6 in it. That's 6 vertex. That can't be. There are all sorts of diagrams. So if you want, there is a discussion of the vertex at 2 loop, not a complete discussion, but just diagrammatics and some basic structure of it in Peskin. Peskin goes over some of the diagrammatics of the 2 loop here. Good. All right. So this is our discussion of 2 loops. This is the only 2 loop discussion we'll ever have until the end of the semester. At least by now you've seen the what needs to be done, right? The tricks are exactly the same. Dim reg, you do these you do Feynman parameters, you expand, you do the integral, and there's a gamma function, you expand around d minus epsilon. And these kn's are basically all over the place because after you do Feynman parameters, you do Feynman parameters so that your integrals look like kn. That's exactly why you do Feynman parameters, right? Because you have different propagators with different momenta propagating, right? By defining a weight function between them, you symmetrize. All right, question. Now we're going to completely change gears and talk about effective action. If I can explain the normalization group to you guys, I think that I consider teaching QFT to a success. And this is where it starts. So perturbative normalization, by now you've seen a set of tricks. But the foundation of what are we doing physically, I have not explained. From now on, we're going to move towards the foundations. Effective action is still a set of tricks you could imagine, but as you get to RG, the concepts will come. All right. Let's go back to beginning of QFT 1. Action in the Lagrangian formulation of quantum field theory was the starting point. You started with a local functional called action. Local means that there's an integral over space-time of a density, which is the Lagrangian density. Now, why do we care about this? Because action is extremized on the solutions to the equations of motion, right? So del S, del phi on the solutions is equal to 0, phi classical. In quantum field theory, the phi should be promoted to an operator, phi hat. And then what would play the role of phi classical? What plays the role of phi classical is the 1-point function of the operator, the expectation value of it. Good. Now, here's a question. Is there a functional of phi classical x that is extremized on phi classical and takes into account takes all the corrections into account? Are you following what's going on? Okay. When you have classical field theory, you have a functional action, you vary respect to phi, and then that's a classical equation. Right? Now, in the quantum world, there is no variation of that type. There are operators and a path integral. But what we would like to do is then that has 1-point function, 3-point functions, and higher point functions. Right? Call this phi classical. What we would like to do is we would like to construct. So now, of course, like the 2-point function and 1-point functions are going to be they're related. You turn the cranks of the theory, and it will generate what it is that all of these guys are calculated. What we're asking is that is there a functional, a phi classical we could write down that has all these calculations in it. So if you want to do the quantum calculation, somebody calculates for you that functional. You just do a variation principle and read off these guys. Right? Now, what would such a thing be? Such a thing would be basically that somebody, in essence, does the path integral for you, right? And at one loop or something, gives things to you, right? But the difference is the following. The path integral was a functional of j, not a functional of phi. The question is, can you construct a functional of phi that does the same calculation? I'm going to walk you through it. All right? At least high level, is it clear what we want to achieve? All right. Let's go back to statistical field theory. This is where things are a lot clearer. Consider classical Ising model. The Hamiltonian is just nearest neighbor spins with some coupling j, and then some on-site terms. The finite temperature partition function is the following: z of, actually I should call this z of beta. For example, I'm intentionally not putting it for reasons you become clear. As sum over all spin configurations, e to minus beta of h of that particular spin configuration, right? Each spin configuration is a microstate. This is classical field theory, statistical field theory, finite temperature field theory. Good. All right. Now, one thing you could do is you could do spin blocking. What is that? So we're summing over all configuration microstates. What you could do is you could define a coarse grain. We could split these spins into blocks, many blocks, and then say the average of these spins in this block is some little m. The average of spins in this block is some little m, and so on and so forth. Now, this is the absolutely important part. The sum over all microstates can be written as a sum over all macrostates. These are macro, different fixed values of m's are macrostates. And then there's a little sum, which is for a fixed macrostate, what macrostates contribute. Let me work out an example. This is the essence of renormalization, by the way. Imagine you have 6 spins, right? So what you have is a sum over S1, S2, S3. I'm intentionally going to write it this way. S4, S5, S6. 6. Right? Then I'm going to define what? I'm going to define these 2 boxes. And I'm going to define a variable M1 and variable M2, which is the average of this 1 over 3 of S1 plus S2 plus S3, and similarly 1 over 3 S4 plus S5 plus S6. So what are the variable values that this can take? The values that this can take go from -1, right, to 1. There is a single microstate of this, which is -1. It's down, down, down. There's a single microstate which is up, up, upwards. Right? In between, you have different values. You have -2 or third, -1 third, third, 2/3, right? And there are several microstates for this. Good. Each of them will have a number of configurations, but these are the options. Similarly over there. So what can you do? You could split this sum as the sum over m's, M1 and M2. Right? And then a sum for all the S given a particular value of M1 and all the S given a particular value of M2. These are macrostates, and these are all microstates that contribute to that macrostate. Good? This is what we're doing. And then you could perform this sum. Right? You perform this sum, and what do you obtain? You obtain, because you do this sum, you obtain, this is a function of m. You get e to minus beta h tilde of m. Right? So as you this is called coarse grain, right? As you coarse grain, your Hamiltonian written in terms of coarse grain variables would not look like exactly like what it used to. If there's a microstates, it will be a new Hamiltonian. That's the running of the Hamiltonian, right? Everybody's with me? It's like squinting a little bit, right? If you have a very, very sharp vision, you see every single microstate, but because you're summing over them anyways, you might first like say, yeah, it's like squinting a little bit. But notice that from the point of view of the overall sum, this is an exact relation. I've not made any approximations whatsoever. Good? Now, if let's repeat this. What we're gonna do is, let's say you have an Ising system, and your Ising system is infinite in length. We're gonna put inside a box. So every spin takes two values, +1, -1. But we're gonna put inside the box many of these guys. What happens when you put the guys, many of these guys? The average becomes a smooth function between -1 and 1. -1 and 1. And that's when you get a field. Right? Now, in principle, it's still not, you don't obtain a smooth field unless the variation from here to here is slow. Right? So for example, if the value of the average here was, I don't know, like 0.14, the average here should not be all of a sudden -1, right? That's a low energy limit, right? You're squeezing a lot of these guys. Why is it low energy limit? Because the Hamiltonian responds to quick nearest neighbor, right? That's what the Hamiltonian responds, right? So this is the essence of the continuum limit. So in the continuum limit, you end up with a path integral over the so-called magnetization field. Magnetization is the average coarse grain variable, right? It's now a functional, right, of e to minus beta h of m of x. Good. Now, to calculate correlation functions, recall what was the trick that we had. We would add a source, right? In this case, we would put the spins turn on some magnetic field, right? So that would mean that you add this beta m term. Magnetization couples to the magnetic field. This is a source. This plays the role of J in quantum field theory. Good. And now you have Z of B. Then why did we do this? Because -1 over beta ln of Z of B is the free energy. If you take derivatives with respect to B of free energy at fixed beta, these derivatives will bring down integral of d of x m of x. So the derivatives of these derivatives will give you the average overall magnetization. Good. It gives you, let's take the derivatives, but not set the source to 0. We're talking about background field methods. We introduce a background of magnetic fields. We take derivatives, right? And then we get M as a function of B, magnetization as a function of the source. Right? You have a bunch of magnets. You have a knob, which is magnetization, background field. You turn it on, and that will make these guys align. Right? But that you don't know what's going on. All you know is that the average magnetization responds as a function. You should compute the response as a function of B. M as a function of B. Good. Now, M is like a 1-point function. Good. It's like phi classical. B is like your source. If you wanted to view things in terms of M as opposed to B, you could just invert this function. Now you know what the response is what is the overall magnetization as a function of the source, magnetic field. Now you say, for what is the magnetic field that gives me this magnetization? Good. That's just inverting it. Now you're talking about a function of the magnetization. This is in lines with effective field theory. Let me pause here to see if everything's clear. But it's just inverting that relation. Yeah.
So what we're showing with the differentiating with respect to the free energy to get the correlation functions, is that showing like what we talked about before, where all of the higher order correlation functions are being built from the 1-point function? Is that the direction we're
Yeah,
going
no,
with it?
they're not being built. So good.
Every time you take another derivative, another one comes down.
Right. So lovely. So 1-point function is a derivative and then set the source as 0. The 1-point function, before you set the source as 0, knows about all the correlators. That's what we're talking about. That's the sort of effective action, right? Of course, once you put the j equals 0, that's just a 1-point function. That's it, right? Good. So, yeah. Now, what is an effective action in thermodynamics, statistical field theory? It's just the Gibbs free energy. What is it? You take your free energy minus log of partition function and add to it MB. Now, why do you do this? Because if you take the derivative with respect to magnetization, right, is now del F del B del M, right? All I've done is that del F del M, I've put in this partial differentiation, plus B plus M del B. But look, these two terms, they cancel, right? Because del F del B is minus M. So what did we construct? We constructed Gibbs free energy is Helmholtz free energy is a function of the source, right? Gibbs free energy is a function of magnetization. Helmholtz free energy, it's a function of source, that is when you vary with respect to the source, it's extremized on the correct magnetization. By varying it, you get magnetization. Gibbs free energy is a function of magnetization that, as you vary with, is extremized on the source value, the amount of source that you need, right? This is nothing but a Legendre transform. You do this in mechanics all the time. Maybe nobody explained it this way to you, but here's what happens. Your Lagrangian in mechanics is a function of Q and Q dot and T. Say, forget about T for a second, Q and Q dot, right? Del Q dot is P. What you would like to do is you would like to have a function that is a function of P, right? That when you vary with respect to P, you get the Q dot, right? P and Q dot are like play the role of source and magnetization. And here's your Legendre transform. You just take your Lagrangian with a minus sign and add to it PQ dot. This is the same mathematics. So it's not true to say that, yeah, it's important that you don't set j equal to 0, right? Otherwise, you just have a 1-point function. The hard-point functions are not function of the 1-point function. But 1-point function, as a function of source, knows about all the higher point functions in the absence of the source. Good? Because as you said, you just take derivatives. And that's what we're doing. Now, what is the sort of effective actions in quantum field theory? It's the exact analog. Let's just talk about Euclidean signature. So you have a path integral over phi, e to minus integral d of x, Lagrangian, Euclidean Lagrangian. And then there's a source that you introduce, jx phi x. Now, the source is at every point. Previous example, you could have introduced magnetic field that depends on each point as well. But For simplicity, I didn't do that, but it's just similar thing, right? Now, if you do this integral and take the logarithm with a minus sign, this is the e2 minus w of j, and we said this in detail. We discussed in detail that w of j is the generating function for the connected correlation functions, right? So when you take a derivative with respect to j, you get phi of x. But here, in the presence of j, right? Good?
Then to make the final jump to classical, you set it to 0? Or...
No, I don't. Well, if you want the 1-point function, you set it to 0. Right. But this is magnetization, right? This is like, this is a function of j. It's we say the 1-point function in the presence of source. That's called the background field method for that reason, right? You had a theory that didn't have any background. You introduce a background, now the 1-point function in the presence of background knows about all the correlators in the absence of background. Right? There we go. Phi classical function of j. Right? Now, what you would like to do is you would like to invert this and have something that computes for you j as a function of phi classical. In fact, what you would like to do is a functional that of phi classical that that's extremized on j. And here's what your functional is. It's just a Legendre transform of the w of j. So you take w of j, add to the integral of d4 of x, j of x, phi classical of x. That's it. And this is called effective action. Now, it is straightforward. It's just partial differentiation to show that del of this gamma, this effective action with respect to phi classical is j of x. In the absence of a source, this derivative is 0. Right? But now what is important is that because we did the path integral, right? This contains all quantum effects. Good? So you want to calculate, say, some quantum field theory, some strongly coupled quantum field theory, you want somebody to describe to you all the correlation functions of that, right? And that requires doing insane amount of work, right? Doing all sorts of Feynman diagrams at a certain loop. Of course, the calculation is done at a particular loop. Instead of, and how do they transfer that information to you? How do they tell you that? All they need to do is to just describe to you a single function. All you need to do to get your correlation function is just take derivatives of this functional, the single functional. That's called effective action. And that encodes already all the quantum effects. Good? All right. So now I have to tell you what this guy does. So first of all, this effective action ends up being a local functional, right? I mean, that's not surprising. W of j was local, and they added something local to it. So if it's local, if W of j is local, right? So sometimes this the density inside the integral is called the effective potential. Now, just a little recap. Well, actually, this is what we're going to say. What remains to be said, the only other thing I want to tell you guys about effective action is what does it compute for you? J calculus is the generating functional for correlation functions. Minus ln of zj, w of j, is the generating functional for connected correlation functions. Gamma of phi classical is the generating functional for the 1-pi diagrams. This is what I'm going to try to argue for in the remainder of this lecture and the next lecture. I'm going to pause here. Questions?
The new step that we did compared to Q of T1 was the second line to the last line.
Yeah.
The other stuff we already did.
Yeah, absolutely.
Yeah.
I'm just comparing this with other stuff, right? But notice where the magic comes from, right? I mean, already this stuff, oops. Already you did this. Already when you said you wanted to calculate, we already saw that partition function was a method to, if you wanted to describe to me all the correlation functions in the theory, you describe to me in terms of a single functional, right? W of j, for instance, right? But that W of j is a functional of the source. I would like to have a description in terms of my magnetization, the thing that I can actually observe.
Then since you inverted it, like there's no need to go through this setting j to 0 because j is not there.
Yeah. I mean, j is not 0, right? J is not 0. You could view it, if you wish, you could view it as, I mean, there's nothing profound about it. It's a way of packaging the data of the theory. What is profound or nice about it is that it's intimately tied to a normalization group, whatever the story I was just telling. So it sets the stage, because it's related to coarse graining, it sets the stage for normalization. By the way, there's another thing that's real interesting here, which is, remember Landau's paradigm of how we started. We said, take your fields and symmetries, take your symmetries, right? And write the lowest, write the action that's local in field and the respects to symmetry and do an expansion to the lowest orders in the field and the derivatives, right? So now, once you put that inside the functional, the path integral, you would have to do path integral. The important part is that, and then what pops out of these, like say effective action, right, after the transformation. Importantly, quantum symmetries are just non-perturbative quantum, have to hold, right? They're just like, they have to hold. So this effective action will also have to satisfy the symmetries that you have. Like, it has to be consistent with the symmetries. All right. So now what we're going to do, I'm going to set the stage for the calculation of why the effective action is the generating functional for the 1-pi diagrams. So, all right. So what is del of derivative of effective action with respect to phi classical? Is j of x. Good. That means that if you take a derivative with respect to jy of both sides, you get the Dirac delta function equals this. Good. Then you take this guy and add this del phi at z. That's all I've done. Nothing fancy. Good. Then you notice this is del w del jz. Good. So you immediately conclude that the j derivatives of del w jz is the connected 2-point function with j. Do you see this? All right. So now what do we obtain? We obtain that this Dirac delta function is an integral over z of the connected 2-point function of j, this guy, right? This means that you have a Dirac delta function, which is an integral of this this is a function of y and z, and then this is a function of z of x. This means that this is the inverse of this guy. Should I explain this part? Maybe I should explain this. This is something that's very useful in quantum field theory. So imagine you have matrix multiplications. What is matrix multiplication? You have A times B, right? IK is A, J, sum over J, B, JK. Right? I and J's these are discrete indices. Now imagine I wanted to construct an object similar to this, where I and j were continuous. Now, the analog of a function would be a kernel, some a of x and y, right? The analog of multiplication would be an integral over y of b of y and z. Right? Now, what is a minus 1? You say you have this relation, right? Is equal to identity. Right? So it means that this ik is delta ik. Right? So what would be analog of an inverse of A? It would be that this is a Dirac delta function of x and z. Right? That's what we obtained. We've obtained the Dirac delta. Well, sorry for I put them y and z different places. Dirac delta function of z is the connected 2-point function on this guy. Right? So what did we find? We saw that the first derivative of the effective action is the source. The second derivative of the effective action is the inverse of the connected part of the 2-point function. Good? So inverting it, you obtain this. Everybody's with me? Now, I'm going to take yet another derivative. So let me come here. What I need to do is I'm going to take another derivative of j here, right? What does that give me? It gives me a 3-point function of j connected, right? That is del j of this expression. I'm going to insert del phi classical integral over y. Once again, I notice that this is a 2-point function, j connected, right? Sorry. Good. What is this del y of this guy to a power of -1? You have this relation. This is something as a physicist you should definitely always memorize. If you have a matrix, and similarly, this is just a variational principle for operators. It's for matrices and operators. So I'm using the same thing. So you have the del phi of this guy, -1. It means that this -1 sits here, this -1 sits here with an extra minus sign, and then the third derivative sits in the middle. Good. What does this look like? Let me show it to you. So what we found was that the 3-point function, the connected piece of it, which diagrammatically is this, right, became an integral, right? Oh, actually, you also notice that these guys are just the 2-point functions, right? So this is a function of x, y, and z, and what is happening is it's sitting. So this is the third derivative of the effective action. The equation is precisely this: is this. Right? Good. This is precisely what it means to be the generating functional for the 1-pi diagrams. Because if you cut here, any cut will make it turn into 2 pieces. Yeah.
Why do we get 3 copies of the 2-point when we die?
Oh, because of this. So look, I did I take one derivative here. That gives me one copy.
Oh, okay. Yeah.
Then from the minus one, I get two other copies, and the locations work out now. Right? So the third derivative of this is the 1pi 3-point function. It's basically G3, 3-point function, divided by G2, G2, G2. Next lecture, we're out of time now. What we're going to do is we're going to go to one higher order, 4-point function, right? Now, what do you expect to see at 4-point function? So you expect to see that the 4-point function becomes what exactly? So there is this piece, right? But then there are other pieces. What are the other pieces? This is also 1pi. The equations are recursive, right? The equation, that's how you prove it. Because if this was 1pi, right? Putting it this way, this is still will contribute to this guy. So we're gonna do this in the next slide. But in summary, what was let me just what happened? Let me just summarize. We introduced effective action as when you had your partition function, that was a function of the source. And you could take minus log of that was the generating function for correlation functions, right? But as a functional of the source, you could try to invert that relation and get the magnetization as a function of and get the source as a function of magnetization, as a function of the field that we call phi classical, right? Now you treat that functional, you work with that function as extremized on the source, right? This extremization gives you the source, and it's a generating functional for the 1pi diagrams. So that's what we're going to talk about. But all of this was about performing the full path integral. So to relate this to this magnetization thing I was talking about, right? So we had these spinors, right? You initially had some partition function, right? That had the sum over all s's, right? Of eta minus beta h of s's. Good. So let's keep track of this. Then you did for some coarse graining and performed the sum. We found something like this, right? It is some coarse grain. Now, what happens if you just coarse grain all the way? So instead of having, like you go all the way, and what you obtain is just the full answer. There's no sum left, right? And that is actually your generating functional. You end up with a functional of M, your effective action. We're gonna see that. All right. Any questions? Not stop this. I posted homework 2 and 3.